So we start with the fundamental thing that we can say about electrical stuff, which is what we call electric charge. So electric charge is something that can attract or repel each other, right? So we know that electric charges exist since a very long time ago, like in the ancient Greek time, so many thousand years ago. So I'm not gonna repeat too much, like the historical development. Only mention a very few important things. So the only thing that we understand or need to understand about electrical charges is that there are two kind of charges. Two kinds of charges. And charges, what we mean is electrical charges, right? And these two kind, nowadays we call it positive and negative kind of charge. So we can maybe draw something like this, positive or negative. But I want to say that you don't really need to name it to be positive or negative. Or you can either call one to be negative instead of positive. You can flip the naming around. You can call it one type 1, type 2 or something like that. Or you call it A and B. It doesn't matter. The only thing that we care is that there are two distinct kind of charges. Okay. And how they interact with each other, that's going to be the main topic for today's lecture. So people know that charges exist, electrical charge exists, but we don't know what it is exactly until someone actually measure the property of the charge. Right? This is kind of related to the idea of atom. So some of you might have studied chemistry in either high school or maybe doing it now. And you know what an atom is? An atom is the smallest unit of substance, right? For example, if you take a block of metal, for example, like aluminum, Al, right? And then what you do is you take a knife, well, maybe a knife doesn't work, like a saw or something like that, and then you cut this block into half. What you will have is still called aluminum, but the size is just half of the original one. And if you keep cutting it in half, and then you repeat the process, your aluminum block will get smaller and smaller. And at some point, you cannot do any cutting anymore because that's the smallest, unit of aluminum that you can have. So that smallest unit, the thing that you cannot divide any further. So I say cannot be divided anymore. That's what we call an atom. Okay, so the concept of an atom is actually very old. It's again same as the charges that is date back to the ancient Greek time. But it's not until like very recently like people can actually see that okay, there's actually one atom and you cannot divide it any further. Okay, so this is the idea that get verified for charges in 1909. So you probably have heard the name Millikan. So he's the one who performed an experiment to measure the the electron charge. So what he found is that the charge is also have analogous kind of property as an atom in a sense that if you take something which is electrically charged, for example, if you have some kind of lump and then it's positively charged, something like this, right? And then you divide it smaller and smaller. In the end, you will get to something which is still positively charged, and then you cannot divide any further. So kind of the same concept as an atom. Right. So this is what we call the fundamental charge. So it's a charge that we cannot divide any further. And we know nowadays that there are two kinds of fundamental charges. One is negative charge, and that is associated with the particle, which is called an electron. And by convention, we call it negative charge. Again, this is kind of arbitrary. You can, do physics while calling the electron charge to be positive, and everything will be the same. Okay. The other thing which we found is that there's also the fundamental charge, which is positive charge, and that is associated with a particle which is called a proton. Right. So electron and proton has, the smallest unit of charge possible. Some of you might know something about, like subatomic particle, like quarks or something like that. We're not talking about that because, strictly speaking, quark, which has, like a fraction of, fundamental unit of charge, cannot exist in a sense that cannot exist freely, so it has to be clumped together. So in a sense, the charge that we can measure in experiment will always be either electron or proton charge to be the smallest, amount of charge that you can have. But in any case, the electron and proton charge, one is negative, one is positive. So we're gonna call this one minus E and plus E, where E tells you the amount of charge, and we're gonna tell you in a moment what it means exactly. So amount of charge. So E is a number. So some of you might be tempted to, think that E stands for electrons. It's actually not. Okay. E stands for elementary charge. And we can measure charges, the amount of charge we have relative, using what we call the Coulomb's law, which we're gonna talk about in a few moments. But we can assign some number to like these kind of charges, like how much charge we have, right? So if you have a lot of charge, then maybe it will interact a little bit stronger than, like less charge. So the elementary charge, which we call E, is about 1.602 times 10 to the minus 19 C, and C is the unit of charge. It's the SI unit, and it stands for coulombs. Okay, so it's just a unit. Again, we will talk about this in a few moments, but we can write down the number like this to be E, the elementary charge, right? And you can see that the charge of electron is minus of this number, and the charge of proton is plus this number. Okay, so electron and proton have the same amount of charge. It's just that the polarity is opposite. Okay, so proton has plus E charge, electron has minus E charge like this, right? And E is this number, so you have to put in plus or minus yourself, right? So if you know that it's an electron, then you put a minus sign. If you know it's a proton, then you put a positive sign or plus sign. Okay, so never think that E stands for electrons and then say E equal to minus 1.6. That will be very confusing. Okay, so you want to be as explicit as possible about the design. Okay, so what did Millikan actually measure? So I'm not gonna talk about the experiment. I'm gonna tell you only that the experiment is called the oil drop experiment. So some of you might have studied this in high school, but it's not so important for us now. The important point from this experiment is that Millikan showed that any charged particle, maybe a piece of dust, many of them. Okay, so due to some circumstance, these dust might acquire some electric charge. For example, it might lose electron, right? So it become positive charge, or it might gain some electrons, so it become negative charge, right? Something like that. But in any case, what Millikan found is that this dust, if the dust particle is charged, then the amount of charge is always going to be multiple of E. For example, if you take dust number 1 and then you measure the charge on dust number 1 by like whatever equipment that you want to use, you might find that the charge on the dust, which most of the time we will use variable Q to stand for charge. Okay, so I would say Q for dust number 1 can be equal to 1.6 times 10 to the minus 19 Coulomb. This is fine because this probably means that the dust lose one electron or gain one electron, so the charge is like this. Okay, so this is equal to one elementary charge. And then dust number 2 might have 0 charge, so 0 Coulomb. That's also fine because some dust are what we call electrically neutral. And dust number 3, you repeat the experiment, you might get that the charge that you measure on dust number 3 is 3.2 times 10 to the minus 19 Coulomb. This is fine, and this means it's equal to twice the elementary charge, so 2e. And then you repeat the experiment many times, you get dust number 4, number 5, number 6, or number 100. No matter how many times you repeat the experiment, you will always see the amount of charge to be a multiple of elementary charge. You will never see, for example, dust number 6 to have Q, let's say, equal to 0.8 times 10 to the minus 19 Coulomb. This is half of elementary charge. No one has seen this. Okay, and we believe with almost 100% uncertainty that this will never be seen in the experiment. You will always see a multiple of elementary charge, 1e, 2e, 3e, but never half of e, 1/3 of e, 5/6 of e. So a fraction of elementary charge cannot be, is not observed ever. So that's a very important fact because this leads us to believe that this charge is associated with some kind of particle. And then we know nowadays that it's either proton or electron. Okay, so a charge cannot be divided into half of elementary charge. You can have a lot of E, but you cannot have half of E or 3/2 of E. So that's kind of the main conclusion from Millikan's oil drop experiment. Okay, so if you are interested, you can do a quick Googling, and then you will see right away what the experiment looks like. Okay, so since we talk about this, elementary charge, and it's associated with proton and electron, so let's talk a little bit about the, physical property of electron and proton a little bit, since it's not only interesting, but it's probably important to know. So let's talk about electron. Electron actually, let me make a table. So I will list here the name of the particle and mass and charge. So the first thing is electron. So electron is very light. Usually the mass of electron is abbreviated using this symbol M subscript E. Okay, so E here stands for electron. So the mass of electron is measured to be about 9.1 times 10 to the minus 31 kilogram. So it's quite difficult to imagine how small this is, right? So we as human being usually has a mass of about, like 50 to 100 kilograms, right? So you need how many electrons to have the same mass as, one adult human being? Well, that's gonna be, 10 to the something like 34 or 33 or 32, something like that, right? So that's gonna be 1 million, million, something like that, number of electrons to be the same mass. Okay, so electron is extremely light. The mass is very small. And the charge is negative E. We talked about this already. Right, so minus E. And again, I write down again here that E is about 1.602 times 10 to the minus 19 Coulomb. So we are dealing with a very small number here because these are, very tiny particle. So this is electron. And next, we're going to talk about proton. A proton is actually a very different kind of particle. It's a lot heavier than electron. So proton mass, we call it MP. MP is actually about 2,000 times heavier than ME. So the proton is heavier. And the mass is about 1.726 times 10 to the minus 27 kilogram. It's a lot heavier than an electron, but still quite small compared to, like normal object that you see in daily life. But most of the stuff that you touch, you eat, you breathe in, the mass is actually coming from protons. Okay, because again, electron is about 2,000 times lighter, so the mass of electron actually does not contribute much to the mass of any object. And the charge is plus E, so let me make it a little bit nicer like this. Electron, proton. And the third particle, which we will mention here, but not going to talk about it too much because it has no charge. It's called neutron. Neutron has zero charge, hence the name, right? Neutron is neutral, electrically neutral, so the charge is zero. So that means it will not interact, electromagnetically with any other thing because the charge is zero. So it's kind of like very inert thing. So we're gonna mention here because it's one of the common particles that you're gonna see in an atom, but it's not so relevant for to us in this course. The mass of the proton, the neutron, we call it Mn. It's actually very close to proton, so it's 1.6749 times 10 to the minus 27 kilogram. So almost the same as proton, except a little bit higher, less than a percent heavier than proton. But nonetheless, the charge is zero, so it has no what we call electromagnetic interaction with any other particle, right? And these three fundamental particles join together to give you all kinds of elements that you can think of. Right? So if you study chemistry before, you know, like different chemical element will have different, you know, chemical property, can form different chemical reaction. For example, the simplest atom that you can form is called hydrogen. And hydrogen is an atom which consists of a proton, P plus, and electron orbiting around a proton. Right. So this is called a hydrogen atom. And it kind of makes sense that it's electron going around proton, not proton going around electron. Right? Because we know that electron is very, very light compared to proton. So electron is easier to move around. So that's why electron is going around the proton instead of the other way around. Right? So think about, you know, like the Earth orbiting around the sun, not the sun orbiting around the Earth, because the sun is many, many times heavier than the Earth. Right? So it kind of makes sense. But if you look at any kind of atoms, for example, let's talk about helium. Helium is the next element in the periodic table. And if you take the periodic table and then you go heavier and heavier, the thing which is different is the number of electrons will increase. So hydrogen has one electron, but helium atoms will have two electrons, right? So the center of the atom is called nucleus. For helium, usually you're gonna have two protons, so P plus, and also two neutrons. Like together, this is called the nucleus. And the electrons orbiting around, we have two. Right, so this is a very rough sketch of what's happening. But in a sense, the number of electrons will always be equal to the number of protons for, you know, like any chemical element which is, you know, appear regularly. Like helium, we all have two electrons and then two protons, right? So the charge of the whole atom will be neutral because you have the same amount of negative and positive charge, so they cancel out, right? So electron is minus E charge, proton is plus E charge, so altogether the charge is zero. Helium is the same. You have two electrons, so the total charge is minus 2e. And you have two protons, so the charge is plus 2e. So you add all together, then you get also zero. Okay, so this is what we call neutral atoms. Neutral atoms means Q total is equal to zero, and Q total for helium or for any element, we also have the total charge to be zero. And now you ask like, okay, but we know that in some case, you know, an object can acquire some electric charge. For example, if you take, again, a lump of, let's say, you know, rubber, So rubber consists of many atoms inside. And if each atoms are electrically neutral, each atom has Q total equal to 0. So it doesn't matter how many atoms you have, the total charge will also be equal to 0. But sometimes we observe that this object, a clump of rubber, has some non-zero charge. For example, this thing can acquire charge equal to, let's say, minus 5e, for example. It's not 0 anymore, the total charge. The question is like, how can this happen? Because we just say that every atom is electrically neutral. So what happened is that even though normally an atom will have the same amount of electrons and protons, but you can force electron to get, kicked out of an electron, of an atom. So you can strip out an electron. For example, helium can become the same helium, but with only one electron. The helium itself is less happy when this happens, but it can happen. So in this case, the amount of positive charge is larger than the amount of negative charge. So the total charge is no longer 0. And in this case, the total charge is positive E, right? Because you have more protons than electrons. So when we say we charge anything, right? So when we charge an object, and this charge is a verb, when we charge an object, it means that we are trying to make the object not electrically neutral. Okay, that's what we mean by when we say we want to charge an object. So when we charge an object, what we do is we either remove or add electrons from or to the object. So what do I mean by this? You can see that you can take away an electron to make the atom to be positively charged. You can do it the other way around. You can actually force inject another electron inside this atom. So in this case, you have more negative charge than positive charge. So Q total will be negative in this case. Okay, so you can either remove an electron or you can put in extra electron to make an atom not electrically neutral. And that's gonna happen when you try to charge an object, right? So you either remove or add electron. So you remove from the object or you add to the object these extra electrons. So in this case, the rubber has total charge of minus 5e. So what happened is maybe someone put in extra electron into this object. And how many do we need? Well, we need 5 of them, right? So someone put in 5 extra electrons of the object. So where these electrons come from, we don't know, but it's probably come from somewhere, okay? So maybe you borrow from a different object, different piece of rubber, where it used to be electrically neutral, but now the total charge is positive 5e. So what I mean is that maybe the 5 electron that you put in the top rubber is coming from the bottom one. So you do the charge transfer here. But since on the bottom one you remove 5 electrons, so the bottom one becomes positive 5 and the top one becomes negative 5. Right? So this is usually what happens when we say we charge an object. Right? You remove electrons from the object or you add electron to the object, right? And that electron is coming from some other object. We also found that we cannot just make an electron out of nowhere, right? You cannot say, okay, I make this object to be negative charge by putting in some electrons, and where does those electrons come from? Well, I just made it up. Okay, that's actually not what usually happens. So usually you need to take electron from some other object if you want to add it to this particular one. So in any case, we're gonna be talking about what happens when you have an object which is now not electrically neutral. For example, this one now is minus 5e charge, and this one is plus 5e charge. What's gonna happen between these two objects? And that's the topic of what we call the Coulomb's law. Coulomb's law. So Coulomb is a name of, I think, French physicist. And the name Coulomb is what we use for the charge, the unit of charge. Okay, so we use a lot of scientists' name as the unit of, physical quantities just to honor them. Like Newton, Pascal, joules, right, watt. Those are all name of scientists. Okay, so what is Coulomb's law? Coulomb's law tells you that between two electrically charged object or particle, there will be a force between them. So let's take one proton here and another proton here. These are two particles and they have some charge, right? They are not electrically neutral. We know that already. And there will be the force between them. And what we found is that if you have the same charge, they will repel. And if you have opposite charge, they will attract each other. So these we have proton and proton, even though they are different color, and that's just the way I choose the color. But they are the same particle. They are both protons. They have the same charge, so they repel each other. So what does it mean for particle to repel each other? It means that from the point of view of each particle, there will be some kind of force pushing them away from each other. So there will be some force pushing on this particle to the left and this one to the right. This is what we mean by repelling each other, is that there will be the force that's trying to pull apart those two particles from each other. And what do we mean by attraction? Well, if you take one proton, but let's say another one is an electron instead of protons. So electron is negative charge, proton is positive charge. So now they have opposite charge. So they're gonna attract each other. Attract each other means the force gonna pull them together, like this. Saying repel or attract, what it means is just tells you this thing. Tell us the direction of the force. That's probably the simplest way of thinking about this is that when they repel, they have the force is pointing away from each other like this. When they attract, the force is pointing into each other like this. And the other thing that we find from the experiment is that the direction of the force, no matter whether it's repulsion or attraction, the direction of the force is always along the line joining the two particles together like this. So what that it means? It means that if you have two charges in general, so I'm not talking about proton in particular or electron in particular. I'm talking about a generic charge. Let's say Q1. Okay. Remember, we always use Q to indicate the amount of charge. Let's say Q1, and just to be very explicit, I'm gonna say this is positive charge. And then I have another charge, which is Q2, and then it's positive also, right? So Q1 and Q2 can be any number which is multiple of electron, elementally charged. So what I say here is that the force between them must be along the line joining the two charges together. So it means that, okay, Q1 and Q2 has the same polarity of electric charge. The force has to be pulling away from each other, right, because they are repelling. The force cannot be something like this. This is wrong. Because what? Because again, force must be pointing along the line that joining the two charge together like this. So the force on Q1 cannot point in this way. Force on Q2 cannot point in this way. Force has to be pointing along the line joining the two together. And that's going to be very important because if you have multiple charges, you need to know exactly which direction each force is pointing, because you have to add them later on. And force is vector, so you need to know exactly the direction in order to find the correct resulting force, right? But in any case, the force on the green one will be to the right exactly like this, and the force on the blue one will be like that. Okay, so that's the direction of the force on each object, each particle. So another thing which I will be very explicit and then try to be as clear as possible is how we label the force. Like in this picture, there are two particles, the blue charge and the green charge, right? I'm gonna call this one, this force F, which is a vector. Okay, so I need a hat, vector hat on top. I'm gonna call it 1, 2. And the green one, I'm gonna call it a force vector hat. I call it 2, 1. So what is F12? This number means something. 1, 2 here. 1, 2 means is it's a force on, okay, acting on charge Q1, which is caused by Q2. This is what we mean by F12. It's the force on Q1 by Q2. If we remove Q2, this force will be gone. That's what we see in experiment. Okay, so in order to see that this force exists, you need another charge. Okay, so this is what we call the Coulomb force. So F12 means Coulomb force between charge Q1 and Q2. So it's always a pair. Okay, if you have this is very important. If you have a single charge and no other charge around it, then you will have no Coulomb force on that charge at all. Okay, so if you have only one charge in the universe, that charge will not do anything because it needs another charge in order to have this kind of force. Okay, so this force is always comes in a pair of charge, right? Only one of them is not enough. So this is F12, and we have here F21, right? So using the same kind of definition, F21, 21 here means it's a force on Q2 by Q1. So remember from last semester physics, when you have force in like the force diagram when you solve mechanics problem, you need to draw the force, and one thing that you need to identify is on what object does that force act, right? So in this case, F12 is the force acting on Q1. F21 is the force acting on Q2, right? So you might be thinking like, why am I so like pedantic at this point? Because it's gonna be a lot more confusing when you have multiple charges. So I want to be as clear as possible at this point that when you write down the force, okay, you have to make sure that it's the force on the object that is supposed to be. Right. So F21 must be acting on Q2 only. If you do something and then suddenly you have some kind of force here, and then it's actually the force F12, something like this. This is wrong because it's supposed to be acting on Q2. So it cannot act on Q1 like this. So it's kind of like a double check whether you have the force on the correct object or not. Okay, so be very careful about this, and you're gonna see why when we have multiple charges in a few moments. Okay, so what else can we say? Well, Coulomb says that the magnitude of F21 is proportional to 1 over the distance between the two charges square. So it's proportional to 1 over r square. This means if the charges are further away from each other, the force F21 or F12 will be equal to, will be weaker in a sense. So the further apart, then the weaker the force is. Maybe I should say this first, that Newton third law, it's been a while since we mentioned this one. Remember what this one is? This one says action equal to reaction. Okay, so looking at this, actually F21 and F12, these are action and reaction pair. So remember what the third law says, action equal to reaction, but they are in the opposite direction, right? So that means F12 is equal to F21 in magnitude, like this. So when you write down the force like this, F12 is proportional to 1 over r squared. You can also add something like this, equal to F21, and all of them is proportional to 1 over r squared. Okay, so r again is the distance between charges. And it's 1 over r squared. So if you double the distance between the charges, then the force will be weaker by 4 times. If you triple the distance, the force will be weaker by 9 times. Okay, so this is 1 over r squared. And the amount of force, how strong the force is, also depends on how much charge that we have. So another thing that Coulomb found is that the magnitude of the force is proportional to Q1 and Q2 multiplied together like this. So that means if you double the charge here, for example, initially you have charge Q1 to be 10e, for example. If you change it to 20e, twice as much, then the force will be double, no matter what Q2 is. Okay, so if you fix Q1 and then you double Q2, force will also be double. And if you double both of them at the same time, because they are multiplying, the force will be 4 times stronger. Okay, so this is what I'm saying. So altogether, you know how to combine this proportionality equation together, right? So force F12, which is equal to F21, equal to, or maybe first, say it's proportional to Q1 times Q2 divided by r squared. This is what Coulomb found, I think, almost like 300 of something like that, 200-300 years ago. I don't remember the date exactly. So it's a very, very old theory and still hold today. Okay, in a very special case that this is not quite accurate, but in daily life, everything that we calculate to make electric, like electronics products or something like that, then this is 99.99999% true. Right, so we need to put in some constant of proportionality, and that's what we're gonna replace this proportionality sign to equal sign, and we're gonna put in a constant here, k. This k is called the electric constant. And it's measured to be roughly about 8.98 times 10 to the 9. What about the unit here? Well, we know that on the left hand side it has to be force, so it needs to be Newton. And the right hand side is k times 2 factor of charges, so that Coulomb square, and then divide by distance square, so meter square. So I urge you to confirm that the correct unit for the electric constant K is Newton times meter square per Coulomb square. Okay, Newton meter square per Coulomb square. And you can see right away why that's the case. Coulomb square cancel with Q1 and Q2. Meter square cancel with R square. And then you're left with Newton, which is the unit of force. Okay, so that's gonna be what we call, well, this whole thing is called Coulomb's law. this equation here. And now there's some details that is good to know. First of all, usually the unit of charge is not going to be in Coulomb, because 1 Coulomb is actually a lot of charge. Okay, usually we don't have that much charge. Usually Q is expressed in micro Coulomb, which is equal to 10 to the minus 6 Coulomb. So before you plug into this equation to calculate the force in Newton, don't forget this factor of micro. Okay, it's 10 to the minus 6. And if you have 1 microcoulomb, another microcoulomb, altogether you have 10 to the minus 12 Coulomb square. Okay, if you forget about this, you're going to get force which is a million times or even million times wrong. And that's not good. Okay, so be very careful about this unit. And just a reminder, one elementary charge is about 1.602 times 10 to the minus 19 Coulomb. So sometimes the amount of charge is given to you not exactly in microcoulomb, but it's given you in how many E's, right? So if you say that, okay, Q1 is 4E, then Q1 is 4 times this number. And you can see that this is a lot less than microcoulomb, right? But it's just different situation. It depends on what we are talking about here. So let's do some very basic example, right? So let's say you have one object here where Q1 is given by plus 2 microcoulomb, and then you have another one which is Q2, another charge, which is now negative 3 microcoulomb. If these two charges are 1 millimeter apart, calculate the Coulomb force, so the force according to the Coulomb's law, on each charge. And when I say calculate the force, you need both the direction and the magnitude, because remember, force is a vector. So let's do the easy part first. The easy part is step 1. Draw the direction of the force. Step 1 is very easy because the only thing you need to care is whether you have the same polarity of charge or not. If they are the same, they repel. If they are opposite, they attract each other. In this case, they attract each other because one is positive, the other one is negative. So we know right away that the force on Q1 will be pointing this way because they attract each other. And the force on Q2 will be pointing that way. So the first step is like a true or false, or like it's a binary question, because it's either going to be pointing this away from each other or it's pointing towards each other. That's the only two choices that you have. Okay, it's nothing to do with the number yet, right? It's just identifying the sign here. So opposite sign, they attract, so the force point in this direction. And now it's probably good to write down whether this is F12 or 21. So this is F12, right? Because it's F on Q1. And this is F21. So it's F on 2. Sometimes you're going to see that people write F12 equal to minus F21. This is fine is just say that the arrow of F12 is pointing in the opposite direction as F21. This equation has nothing to do with whether the force is attractive or repulsive. Because if you have the same force, F21 will point that way, and F12 will point that way. So they are opposite anyway. Okay, so this is true no matter what kind of charge you have. So most of the time it's not really that useful to us. It's just saying that the charge on each, the force on each charge are opposite from each other. Right? But it doesn't tell you anything about whether the force is repulsive or attractive. Okay, so I'm not going to say too much about this. Anyway, that's the first step. The second step is just to calculate the magnitude of the force. Okay, so we get the information about the direction, so that's halfway done. But force needs magnitude also. So magnitude is easy because the magnitude of the force F12 or F21, they are equal, right? So it doesn't matter which one you pick. So just writing down just to be clear. It's equal to K times Q1, Q2 divided by R squared. So this is quoting Coulomb's law. So let's just plug in the number in the right unit. So 8.98 times 10 to the 9, that's for K. It's in the correct unit here. I'm not going to write it down. And then Q1 is plus 2 times 10 to the minus 6 microcoulomb, right? So this minus 6 is microcoulomb. And then times this Q2, which is negative. You can leave the negative sign in, but in the end, we don't really care about it's positive or negative. We only care about the magnitude. But it's good to leave it in anyway. And then you divide by the distance square. And distance we have is in millimeter. Again, you have to convert this to meter. And 1 millimeter is 0.001 meter. And that's going to be square. And then you just plug into your calculator. So I'm going to do that. And then we're going to take a break soon. And then what I get is about 5.4 times 10 to the 3 Newton. Okay. Again, I kind of ignored the fact that it's a minus sign here. I mean, the thing is that we are calculating the magnitude, so the sign here is not so relevant at this point. Okay, so I'm not going to write the minus sign down because it's the magnitude of the force, so it's always positive. Right. So this is kind of, very fundamental example how to use Coulomb's law. Okay, so it's probably a good time to take a break. So I'm gonna set a timer for 10 minutes and then we come back and continue our discussion. All right, see you soon.